Today we're going to see very quickly radioactivity and explain the main things you should know about radioactivity. The first thing that you have to know is that elements in nature differentiate themselves by the number of protons that they have in the nucleus. So you know that an element has a core and nucleus where you have the protons and neutrons. That's where the mass is, and then you have electrons going around. So if you look at the periodic table, you will see that the elements are positioned in the periodic table in this way, and there's a number on top of them, which is the atomic number, and it's equal to the number of protons in the element. Okay, so something that differentiates an element from another is the number of protons in the nucleus. Okay, so if you could change the number of protons in the nucleus, you could basically change something from one element to another. So you change substance from one type of substance to another. So I could basically, in theory, convert lead into gold or wood into gold. It's not so easy, and I would spend so much energy that it's not worth it. But basically, you could convert one element into another just by adding or subtracting the protons in the nucleus. Okay. So what happens in radioactivity? In radioactivity, some substances are what we call radioactive. It means that they don't stay stable in the configuration that we know that they have in the periodic table, but they start losing particles, and so gradually converting from one to the other, from one substance to another, from one element to another, and that is called radioactive decay, because they normally lose particles. Okay, and some substances, as I said, they're the ones that are separated. They're separated from the periodic table. They're the radioactive ones, and you know most of them. Uranium. I can show you here some thorium. Normally, if you have the periodic table, they're right down below. Those are what we call unstable because they normally don't stay in their initial configuration, and they suffer a radioactive decay. There's three types of radioactive decays that you need to know. There's the alpha, there's the beta, and there's the gamma. And it's the ones that we are going to look at today. Alpha are represented like this. Beta, they're using the Greek letters for alpha, beta, and gamma. Okay? So we must know a bit of the three of them, how they work, what they mean, and examples. Okay, so let's start with the alpha. In an alpha decay, basically what the element, when an element has suffers an alpha decay, what happens is it will lose 2 protons and 2 neutrons. Okay. So, if you look at the periodic table, an element that has 2 protons and 2 neutrons is this one, helium. It has atomic number 2, so it has 2 protons, and the mass number is the number of protons plus the number of neutrons. So, 4 minus 2, it has 2 neutrons. So this is 2 protons, and 4 minus 2 equals n neutrons. Okay, equals 2. Okay, so that's basically an alpha particle is basically something like an helium particle because it has 2 protons and 2 neutrons. And what is going to happen to my substance is that it will basically lose 2 protons and 2 neutrons. Let's look at an example. So an example of the alpha decay. We have, for example, uranium with 238 here, and 92 here, which means it has 92 protons and electrons if it's stable, if it's not charged, sorry, and 232 minus 92 neutrons. Okay, so what's going to happen now is it doesn't stay like this, it's unstable, so it will lose an alpha particle and it will become another element because it is going to lose protons. As it loses protons from its nucleus, it is not the same element, it will become another one, which is basically thorium 90. Well, I don't have to look at it, I could look at that. And what we can express this both this way. There's alternate ways of writing this, or you can see it this way, which is showing the particles that it loses, or you could see it this way, and all of them represent the same alpha decay. Okay? So basically what this is telling you is that I had uranium with 92 protons and 238 protons plus neutrons. I am going to lose an alpha particle. It's going to decay. It's going to lose 2 protons and 2 neutrons. So as it loses 2 protons, it will no longer be uranium. If you go to the periodic table and you look at the element that is 2 atomic numbers to the left, you'll see it's thorium. So it's thorium 90, and it's going to lose also another 2. Not only 2 protons, but apart from the 2 protons, 2 neutrons. So in the mass number, it will be reduced in 4. So now it's 238, 90. Okay, and you can see it like this, where it doesn't really show what it's losing, and you must know that the alpha is 2, 4. But sometimes they give you the alpha and they give you the atomic and the mass number, and sometimes they give it to you in the way where it's as if it were an helium particle with 2 and 4. Okay, so this is basically what is happening with an alpha decay. It's losing 2 protons and 2 neutrons. Okay, what will happen? I will give you another very quick example where the thorium that we saw was 90 and 234. 230 in this case. Okay, but as it's 90, it's thorium. It's going to become radium with so that loses 2, so it's 88, and that loses 4, so that's 226. Okay, and it's going to lose an alpha particle, which I'm going to represent like this. The types of exercises that you will see are basically where you will have, for example, something like this, and they say complete these numbers, one or both, and you have to know that as it's an alpha decay, it loses 2 protons, so this becomes an 88, and as it's an alpha decay, mass number, it goes down in 4. Okay, and any other combination of question where you have to know what type of particle is an alpha particle. Beta decay. What's a beta decay? A beta decay, it's a bit different. You have a nucleus where you have the neutrons and the protons. Okay. And what's going to happen in a beta decay is one of the neutrons is gonna divide itself into a proton. So that's an electron and an antineutrino, which you don't really have to know. Okay, it will no longer be a neutron here. It will become a proton, and the electron and this part of here, the electron antineutrino, it will get rid of it. Okay, so basically what is happening, as you see, the number of particles in the nucleus will not change, so the mass number is not going to change, but the number of protons is going to go up in 1, so the element will be different, and the atomic number is going to increase in 1. Okay, so let's look at an example. That's in a negative beta decay, where it emits an electron, which is the most common one. So let's look at an example. If we look at an example, so if we said that this can be represented as either this, that, or this, okay? So beta can be represented as it loses one, it gains one proton. As it gains, we put it as negative, or we can also see it as this, because it's being emitted is an electron. Okay, so let's look at an example of beta decay where the in a negative beta decay where the thorium is going to become which we saw was 90 and to 34 in this case. Okay, it's going to decay to become 90. I'll put the numbers there. So if we look at the periodic table, between the we've got the uranium here, and to the left, 2 places to the left, we saw it was the thorium, and in the middle of between the thorium and the uranium, we've got the protactinium, which is this, and that's got 91 as the atomic number, and we will just keep that, and we are going to put here a beta particle. Okay, so what is happening here? We didn't need to know this, because as they said that it was a beta decay, we know that a neutron is going to become a proton, so the number of protons is going to increase in 1. We're going to emit an electron, so another way to put this is this. Okay, and this is going to go effectively. We are this is not going to change, because even though we are losing 1 neutron, okay, we are gaining 1 proton, so a proton is becoming a neutron. So the one we were losing 1 here, so that's 233, but we're gaining a proton, so that's 234, so that doesn't change. So that's why we represent the beta as 0 up, because it doesn't change, and -1 here, because instead of losing, it gains 1 proton. Okay, and it emits. Remember that a neutron was becoming a proton and an electron. This one, it stays here, and this one is emitted in the decay. Okay, that's in the negative beta. In the positive beta, this is a positron, and it's not normal that you will see it in exercises. Okay, so gamma. What is a gamma particle? A gamma particle is basically a photon. So a gamma particle has no charge and no mass. Okay, and they normally don't happen. The decay doesn't happen individually. It happens with other decays. So, for example, let's look at the one we saw in the alpha one, where there was an alpha decay and this became thorium. It's an alpha decay, so that's this. As it's an alpha, it loses 2 here, and that's this. So that's what happened with an alpha, and at the same time we're having a beta decay where we're losing the 2. You don't have to know. They will tell you. But with a beta decay, with a gamma decay, the numbers don't change, because it's just a photon that is emitted. It's just energy. The protons don't change. The electrons don't change. The neutrons don't change, so the substance does not change with the gamma decay. Substances change with alpha and beta decay, okay? But gamma decays don't normally happen individually, they happen with some of the other decays. Okay, so this is if we have an exercise on how to change the atomic and the mass numbers of a radioactive decay. The other thing that you have to know when you're looking at alpha, beta, in exams at alpha, beta, and gamma radioactive decay is not only and this is for theory, questions, short questions. First of all, the mass, okay, but most importantly, penetration power, okay, and the ionization power, I think, was the other one. Let me check. Ionizing power, yeah, ionizing power. Yeah, so the penetration power is are they strong enough to penetrate which kind of substances, which penetrates more than the other decays, and the ionizing power is its ability to convert other substances in ions, so its ability to attract negative charges of another, positive or negative charges, mostly negative charges of other elements. So is it powerful enough if it goes near an element to take a charge away and make that element become an ion? Okay, so more or less, if we talk about atomic mass units, so any unit, an alpha particle, remember, was going to be 2 protons and 2 neutrons. Protons and neutrons do have mass, so this is more or less for atomic mass units. Okay, remember that the beta was 1 proton, and it was 1 proton. It was an electron that was being emitted. So the particle that is being emitted has a very, very low mass, the one of the electron, which is more or less 1 divided by 2000, I think, yeah, amos. Okay, and the gamma is basically a photon, is pure energy, so it's no mass. Okay, it's only energy. Okay, so it's basically 0. Okay. The penetration power, okay? So what we have to know is that the alpha particles have very low penetration power. Basically, your skin or a piece of paper can stop an alpha particle. So a question in theory could be, if we put a radioactive, alpha radioactive emitter in something that emits alpha particles and a scanner here, a radioactive detector, if we put a piece of paper, which particles will it stop? Well, alpha is stopped by either skin or paper. It's got very low penetration power. Beta, it's got medium penetration power, and it's stopped, for example, by either wood or aluminium foil. Okay, and gamma has very high penetration power, and for example, it is stopped by lead. Okay, so if we talked about a piece of paper, a piece of paper would only stop the alpha; it wouldn't stop the rest of the particles, and lead would stop all of them, and wood would stop beta and alpha, for example. And then ionizing power. Remember that gamma is just pure energy. It's got no charge. So basically, the ionizing power of this is very low. Beta is an electron, so it's medium. Okay, and this is very high because remember this was 2 protons, so it's got a very high ionizing power. It's got more mass than the other ones, and it's got more charge than the other ones. It's got 2 protons, so it can basically easily remove electrons from elements. Okay, so between what I explained of the atomic mass numbers with the decays and this chart, you should be able to solve all the problems about radioactive decay.